Okay, so this video is going to be a little bit different than some of the other videos that we had. Ordinarily, what I'll do is I'll talk about something on the video that leads up to some of the activities that you do that are associated with this video. This one's a little bit different. The in-class activities are mostly going to be extensions of what we did in section 6.1. So if you wanted to, I don't want you to skip this video, but if you wanted to skip this video and go to those activities, there'll be nothing holding you back from doing that. You'd still be able to do them just as well. What we're going to do in this video is briefly discuss a new issue that comes up in 6.2 that is important but is not, life threatening. Specifically, we're going to talk about how we define when two functions are equal. All right, so first thing we're going to do is we're going to recognize that there may be more than one reasonable way to define when two functions are equal. We have to choose one of them because they're not consistent with one another, but it's important to realize that when we're making definitions, oftentimes we are making decisions, some of which are pretty subjective. And then we're going to define the conventional version of when two functions are equal and look at an example. All right, so here are four functions for you to think about. So I have f going from the natural numbers to the natural numbers given by f of x equals x squared. We have g, which is exactly the same, except it's from the natural numbers to the integers. We have h, which is, well, exactly the same, except it's from the integers to the natural numbers. And we have k, which is exactly the same, except it's from the integers to the integers. And the questions you might ask is, which of these functions are equal? Well, we got to think about what equal means in the context of functions, right? So one way of thinking about this, or one issue that we need to think about, is equal functions should be identical in all the ways that are important for functions. So all the functions above have the same formula. That's actually encouraging. That's something that has to be true about functions that are equal. Not enough, perhaps, but it's one step in the right direction. Question is that enough? The answer is no. The equal functions should have the same inputs and outputs. So, for instance, if you look at f and h, they have different inputs. F accepts only natural numbers, but h accepts all integers. Even though the formula works for all integers, if you tried to put a negative number or even 0 into f, it wouldn't give you an output because that's not part of the domain. So that means f is not equal to h, and similarly, f is not equal to k because they have different domains. G is not equal to h because they have different domains, and g is not equal to k. So not all those functions are going to be equal. Well, okay, what about f and g? They have the same formula, they have the same inputs, they have the same outputs. And now when I say the same inputs and same outputs, they have the outputs, each input goes with the same outputs in both functions. The only difference is the codomain. And so we have to ask ourselves a question. Does it matter that they have a different codomain? Is that going to be the thing that makes them not equal? Or are we going to say, look, the inputs and outputs are the same, so that they should be equal? Well, that's a choice that we have to make, right? And I'll tell you right now, from an objective perspective, neither choice is, I think, in my opinion, superior to the other, but we have to make that decision and we have to agree to it, because otherwise when one person says two functions are equal, we want another person to be able to interpret that phrase correctly or accurately, interpret their intent. All right, so the convention we are going to use is equal function must have the same codomains, which means that no two of the above functions are equal. Even though they all have the same formula, some of them have the exact same inputs and outputs. However, none of them have both the same inputs and outputs at the same time. All right, so here's our definition of what it means for two functions to be equal. Let f from the set A to the set B be a function, and g also from the set C to the set D. We say that f equals g precisely when the following occur, and all of these have to occur. First of all, A has to equal C. They have to have the same inputs. B has to be equal to D. They have to have the same, not just outputs, but the same codomain. And f of x equals g of x for all x in A. And again, since A is equal to C, also for all x in C. Those are saying this exact same thing. So equal functions have the same domain, the same codomain, and each input has the same output for both functions. All right, so let's look at the function f from the real numbers to the real numbers given by f of x equals to the absolute value of x. And let's look at g from the real numbers to the real numbers given by g of x equals square root of x squared. Notice that both f and g have the same domain and same codomain, so that's not going to be an issue as far as whether f and g are going to be equal or not. In fact, the only thing that we have to really deal with, since they have the same domain and same codomain, is whether the inputs and the outputs match up the same in both functions. So anyway, f and g have the same domain and codomain, so that's fine. So we just have to check if the inputs and outputs match up. So let's take a look at g, right? When we take g, we get an input of x, and the output, the first thing we're going to do for the output is we're going to square x. And we should note that when we square x to get x squared, that's always going to be a positive number, or I should say a non-negative number, because x could be 0. So when x is greater than or equal to 0, right? So we have, I mean, what we get out of it is going to depend on whether x is greater than or equal to 0 or less than or equal to 0. When we take x greater than or equal to 0, we square it, and then we take the square root. That'll bring us right back to x, right? Because if I take a number like 5, I square it to get 25, the square root is 5. Those are going to be identical. However, when x is negative, square root of x squared so x squared is going to be positive, and when we take the square root of that, that's also going to be positive, but with the same magnitude as x. So when I take negative 4, for instance, I square it to get 16, and I take the square root of that to get positive 4. The 4 and negative 4 have the same magnitude, but they have opposite signs. So what happens, what that tells us is that the square root of x squared is actually negative x. And that may look weird because you think, wait a minute, square root of x squared, that's a positive number. How can we get a negative x? Well, remember, x is negative. So when we take the negative of a negative number, that actually gives us a positive number. But if you look at that formula, when x is non-negative, you get x. When x is negative, you get negative x. That is precisely the definition of the absolute value of x, which tells us that even though the formulas for f and g look different, they're actually the same. G of x is actually equal to the absolute value of x for all x in the real numbers, which means that f and g are equal functions. All right, so now go ahead and work on the activities for more function examples. Remember, these aren't going to be totally focused on whether functions are equal, but they are extending some of the ideas that we had from section 4.1. And then when you work on that one, there's another one called cardinalities of domain and range, which is also an extension of ideas from 6.1. And those are both on the PDF files included with this video.